Okay, so now in case of well testing, what we initially try to understand, let's say if it is a drawdown test, we allow the well to flow. So what is there? Initially, we got the compressible zone within the well. Okay, then it is coming to a skin which is around the wellbore. Then we are getting a continuous or infinitely acting reservoir, and then we are getting the effect of the boundary. So what is happening in the normal case in this present discussion or today discussion, what we will try to see, we will try to see how the graphs are changing right from the initial stage, and then it follows actually in the subsequent section. And then in this particular domain, it may be homogeneous, it may be heterogeneous, it may have fault, it may have so many types of reservoir section here, and then it will be affected by the boundary. So that means the pressure values will initially give us the information regarding the wellbore storage effect, then it will give information about the skin, and then it will give you information regarding the normal reservoir, followed up by your different types of late time effect, maybe the boundary effect. So this is what is there. Initially we have discussed regarding the wellbore storage effect as well as the skin part also, why, what are the different types of skin which may affect your flow behavior. And then we are getting another part which is called the normal reservoir domain. So whenever in the subsequent classes we will discuss the diagnostic flow, actually each and every domain or the pressure graph, each and every pressure graph is now giving us some information regarding this normal reservoir, and we will discuss that time afterward. Okay, so with this big background, I'll just start with my discussion here, the conventional. So how do you understand, or how do you analyze our well test? So if you see, initially we had this disturbance in our pressure recording, but as we move away from the well, the compressible zone actually move out from the skin. So once we move out from the skin, then generally the generally the reservoir, in case normal reservoir, but other case what we do, we just get a different formulation. So what it is there, so if you see during a well test on an infinitely homogeneous reservoir, two flows can be seen if the test lasts long enough. So flow that is related to wellbore storage is the very early stage, or maybe the skin, and then when it is touching the normal reservoir domain, we are getting the infinitely acting domain, and that the responses varies depending on the type of reservoir present. It may be a fractured reservoir, it may be a reservoir having fault in sealing fault, non-sealing fault, or it may be of different types of reservoir signals. Okay, so that is how we'll discuss in our diagnostic plot, and each and every, and the graph, most of the cases we try to find out a straight line. Okay, but in many cases it is not straight line also. So now what we do, the graph shape we try to match with different polynomial form, and the power of the polynomial, or maybe the slope, which help us to identify different physical nature around the wellbore or maybe in the reservoir domain. So three flow rates conditions are examined. One is the drawdown test, another is the build-up test, or the last one is the test following any numbers and any type of previous flow rate. So you may have an last build-up or maybe last drawdown, but before that you may have so many types of test or maybe the production also. So that means we may conduct our test in the early stage of a well, or maybe subsequent, or maybe after 5 years of production, 10 years of production, we also conduct the test. So that is how each and every case our interpretation methods or interpretation methods are different. So if you see the equation, this is a normal equations or diffusivity equation in exponential integral form. We have discussed in detail, and how we have approximated that we have discussed also that. So okay, so depending on the R and T value, we discussed when the this X value, which is R square by 4T. Okay, so this value actually depending on the value of that X, if it is less than 0.02, if it is more than 10, or if it is in between 0.02 and 10. So different types of approximation we followed in our solution. Okay, so now if you see the last equation, the del P, Pi minus PWF, which is recorded in our electronic memory gauge, you see it's an logarithmic approximation formulations. Okay, so by using different formulations, we try to understand what is happening. Okay, so you see different forms are written here with different units. The first one and in the SI practical US unit, and the second one is metric unit. This is the same formulations, but the units are different, and the last formulations is in the form of dimensionless equations. Okay, so T is now converted to TD and P is now converted to PD, and you have the skin for also in the formulation. So what is happening? How do you get the M? So what initial flow inside the well due to your wellbore storage effect for different types of fluid and the skin around the wellbore may be the disturbing. But once you move out from the skin, the basic philosophy is your compressible zone is moving away from your skin part, and that time we generally consider it's an homogeneous reservoir. So that's why we try to expect this Q which are producing at the surface may be supported by our reservoir, and that may be following a straight line. So that's why it may be a normal pressure versus time graph in general, but in many cases we use semi-log plot or sometimes log-log plot. So to get the straight line, what we do, we change our different basic your follow different plots, maybe log-log plot, maybe semi-log plot, and we try to use different formulations or equations. As if you see here, if the pressure measured at the bottom of the hole is plotted on a graph versus the logarithm of time, a straight line with the slope of m can be observed once the wellbore storage effect is ended. So if I just show you a graph, so if you see this graph, it would be very easy. It is pressure semi-log. Pressure is in normal scale, and if you see the x-axis, that is in log scale, del T hour. So if you see the dotted line, which is actually the measured pressure, and once after some time, it is now following a straight line. So that means, and generally we measure the skin generally in the straight line domain, but not in the. Why we measure the skin? Because if you know what is my restriction, then when the restriction is not there, that time we measure the skin. So these are the formulations which we can use to get our normal reservoir part. So if you see the slope of the graph along with the Q and other petrophysical parameters will help us to get the KH, normal reservoir KH. And once we get the KH, so by using formulations, we got our skin. Okay, so the skin value is usually computed using the pressure measurement on the semi-log straight line domain. Okay, so this is semi-log straight line domain. So care must be taken to read the pressure at 1 hour on the semi-log straight line and not by interpreting among the measurement point. Okay, so you see here the straight line on 1 hour. This point we consider for measuring our skin also. But you see here the basically your part has been moved further away from 1 hour. So what can happen actually when we are measuring our pressure? Many disturbance or maybe skin cannot be the compressible zone cannot move beyond the skin also. That's why you see, that's why 1 hour, sometimes we generally taken standard for 1 hour, but it may not be same for every time. So that's why you should see the straight line domain and then extrapolate it towards the pressure axis, and when it is 1 hour, that value we should consider for measuring our particularly the skin and the reservoir KH. Okay, so now the pressure buildup. So what Horner method is nothing but we are changing the plotting pattern actually. Most of the information of the well test comes from interpreting the pressure buildup. So if you see in this diagram, we have TP. Here is the TP. TP is the production time. So in many cases actually, the well test, sometimes we could not perform in the initial stage. We allow the well to flow for some time, or maybe let's say after a workover job is done, we take the test, and that time is really hard to get the initial information. Okay, or maybe how. That's why what we do, the TP is the production time. This is an average production time. It may be 5 years sometime. So that's why interpreting a drawdown test is limited. So most of the cases we do the build-up test, but the drawdown test is limited by flow rate fluctuation. So two differences are there in your particularly build-up test and drawdown test. Build-up test, your flow rate is 0. You are closing a well, so you can well control That means that your flow rate is 0 and you are getting the pressure graph accordingly. But in case of drawdown part, we maintain a stable flow rate, but that is not always possible. So that's why pressure recording are always in fluctuating mode. That's why it is always better to have a build-up test rather than a flow drawdown test. The fluctuation cause pressure variation that are greater near the end of the test than the pressure variation due to the initial change in the flow rate. Okay, so that means, but in case build-up case, it is very much possible. Okay, so if you see, these are the formulations in the build-up test. So if you go through the equations, you can easily understand Pi minus PWS. That means this is the delta time. The delta time is nothing but the last build-up. Okay, this is the last build-up. But what is P? Here P is the production time. That means the initial production. So that P, we have to understand if the production is different times they have produced. So that we have to cumulative way, we need to take the flow rate, average flow rate, or maybe somehow you have to manage how much production is done and how much time it has flowed. So that's why if you divide it by your production time and the total production, you can get a Q, particularly this line Q and the TP. Okay, so that is actually the normal part which we get from our production data and the production time. Okay, so now the same formulation, the variation in flowing pressures are given by the following, the same formulation, putting your normal, these are the field unit, all they are field unit, and this is the TP formulation. So this is initial formulations. Initial means logarithmic expression of your del P, and this is in case of your Horner way of doing the things. Okay, so replacing the two right hand terms. Okay, these two terms, okay, equations of the above equations by semi-logarithmic expression, the radial flow gives you the, once you are changing it, so you are getting this formulation. So this is actually your Horner time. So what we try to get certain this actually this graph. Okay, so you see here you have a Horner time versus pressure. Okay, so Horner time having two different important information. One is your TP, another is del T. So what we do, different way, we just plot it and try to get so linearly. So we try to get a straight line in this plotting also, to get the particularly the different parameters of a reservoir. So one is again the same formulations we use to get our kh. Okay, m we get from our plot, and other formula q your flow rate, you know, b is the bo actually, mu you know, and kh we take out from this. Okay, thickness we know, so k, this is the reservoir permeability, we try to take it from here. So as the drawdown, the value of the slope m is used to compute the reservoir kh. So by using the straight line portion in the your Horner plot also, we try to get the reservoir normal kh, and by using these formulations we can get. Okay, so how do you get the skin value is computed by putting your whatever value you are getting. Okay, so the skin value is computed from the difference between the value of the pressure recorded after 1 hour of the build up on the semi-log straight line. So you see here the same thing. So if you just see here del P plus TD, so what your time actually coming in this time is the infinite so time. Okay, so this is what this is 1, and as you move out, this is actually varying, and depending on the production time as well as the delta time. Delta time is your test of the last test. So you can get, so one is you are extrapolating this one. So this is 1 means what? 1 means your basically your delta is very high. If your delta is high, that means you are coming closer to 1. Okay, so that means the initial product, that means you are taking, that means you are doing an extended period of your drawdown build up test, so that you are reaching at least the initial pressure, which are now considered as a P star. Okay, so that's why we are, by using the Horner plot, we try to get the initial pressure of the reservoir, but most of the cases we generally don't get other. Okay, so by putting the H value, or maybe you can see the in this formulations we have our parameters. So by putting the values we get, okay, that this is usually negligible compared to other terms, this value. Okay, So now extrapolated pressure, I already told you. So this is the normal your Horner plot. So del T is infinite, means in the last segment of your build-up study, you are doing extended period of your build-up so that you are reaching your del T is infinite. So once your del T is infinite, you are getting this point is 1. So that means when your this value is 1, 10 to the power 0 means 1, that means you are reaching approximately to the your initial reservoir pressure. Okay, so during initial test, the amount of fluid produced before starting is usually negligible compared to the amount of oil in place. Okay, so if the pressure buildup was continue indefinitely, the bottom hole pressure would be equal to the initial reservoir pressure. So that is the consideration we take, or we consider to understand. Sometimes what happened after the perforation of the well, sometimes we could not measure the static bottom hole pressure or the initial pressure of the reservoir. So then what happened, we allow the well to flow for some times, but that is not recorded in many cases. So that's why after that we do an extended period of shut-in or maybe shut-in period, so that we can understand the PI, because most of the reservoir cases or every reservoir cases we initially understand particularly the initial reservoir pressure. Otherwise, everything, that means your material balance calculation, even every bit of things would be a problem for you for doing that. Okay, so it is used to compute the average reservoir pressure when production is not negligible. So that is how we are trying to get. Okay, so what is MDH plot? MDH plot is more or less similar, but we are now changing a bit. So this is what is TP plus del T is equal to TP. That means what here? The expression is in the simplified form whenever the production time TP is large compared to the pressure build-up time del T. Del T may be a 1 day, maybe 24 hours, maybe 48 hours or 72 hours, but sometimes it is not reaching. So in that case, your TP plus del T is considered to be TP. Okay, so that means now you are changing your formulation, the same Horner formulation in this form. Okay, so the bottom hole pressure varies linearly versus pressure build-up time. This means that during build-up, the pressure drop due to previous production is disregarded. That means what is initially we are considering, that means the production time and initial part, the whatever production or pressure production, the down is not considered. Okay, so now the two things here, one is your build up and one is your MDH. Okay, so this del P is your real build up, because and this MDH, because whatever pressure initially we have decreased, that we are not considering. Okay, so that is, there is a difference between del P and del P MDH is negligible when del T is small compared to TP. So TP means this production time is so big, so high, that means let's say 10 years you have taken the production from the well. That is how you cannot be, or it cannot be properly understood. Okay, so there is a difference, negligible difference. So at the beginning of the build up, the difference is less, but as we move out during the build up, the difference is more. So these are some of the considerations when we are trying to do so. Okay, the pressure varies linearly versus the logarithm by the plotting of MDH. Also, a semi-straight line with the slope m can be seen once the wellbore storage effect is ended. So this is very important part. Now what we are generally, or we discussed earlier also, wellbore storage effect is generally passing through the origin of your normal pressure versus time plot, because we are considering well is or wellbore is a tank and we are reducing at a specific rate. But there is so many type of flow is there where your it cannot move through the origin, or you may have support. So you may have some positive movement, you may have a negative movement. So initial part also, so many disturbances are there. We'll discuss this in the subsequent class when we are discussing the particularly the diagnostic plot. Okay, so by using your straight line domain, we just get our KH, that means reservoir normal KH, and by using that KH in this formulation, we get the skin. Okay, so the advantage of this method is that it is very simple. However, it is two major drawbacks. It cannot be used to find out the extrapolated pressure. But what is happening in that case, you have your TP plus del T by del T. Okay, so that you can use to get your pressure if you do an extended period of your build up. But in this case, what we are considering, the production TP is more, whereas the del T we are considering very negligible compared to the production time. That's why it cannot be used for extrapolating your P bar or P star Okay, it cannot be used on, it can be used only for values del T that are small compared to TP. That means your production time is very big compared to your test run. So that is how you can use your MDH plot also. Okay, so when production time is short or close to del T, so in that case your build-up points are located under the theoretical semilog state line of in the MDH representation below. So if you see here, this part is your MDH build-up study. So some semilog part, again you are getting a disturbances here. Okay, so that means what is the important part here? We are now trying to find out, let's say, straight line. But in most of the cases, now the present situation is to understand many different situations. We generally don't get this straight line in any cases. So what we get different slope and transition, different slope. I mean, the slopes are not even the straight line. It is a curvilinear sometimes. Okay, so that means the zones are varying. So now this old method is now people are not using, trying to understand the pressure values with time and the derivative value with time, and trying to understand what is the physical scenario around the wellbore or around the well. Okay, so this is what okay, so now after varying flow rates, that means once what we have discussed now, the last build up and last drawdown with respect to the production time, we use Horner time, we can use the semilog also, and we have discussed early classes regarding pressure versus time plot. So now if you see, we have many flow before the last build up of the production. So a test after varying flow rates is interpreted using the flow rate superposition principle. That means many way in different times, let's say TP, total TP and QE got and get a normal graph. But if let's say you have varying production rate and different times, so that's why you use the superposition principle to understand that. So if you just see, we have here QI minus 1, so different flow rate we have a summation. So I stands from 1 to n. So if you have n numbers of flow rate and for different or maybe a duration of different times, that you can add up in your formulations and get their formulation right here. Okay, so if you see here the similar formulation, but you have a lot of flow rates and their durations are different. Okay, so the same formulations, the interpreter is interested in the pressure variation since the last change flow rate. So you can see the pressure variation. Okay, so the pressure build up since the time when the well was shut in is expressed at this formulation. So this is T time, this is n minus 1 time, and now using different flow rates in different time, we can just change our formulations. Okay, so del T is the time elapsed since the last change in the flow rate. So if you just go through, because you may have a lot of flow rates, so we can use the superposition formulation to get. So other things are very simple and same. Okay, so that is how what we do. We use either the last build up with TP as the total production time, and sometimes semi-log. Most of the cases Horner time and your normal semi-log plot, and we try to use the straight line domain. Okay, so the same thing. Okay, so by using that you can get the superposition. So in the x-axis you see you don't have any time here, either your Horner time or maybe the normal del T, where you have a superposition time. So if the values of the present pressure measured in the bottom hole is the pressure versus the superposition function, a straight line of slope m can be seen once the effect of wellbore storage is ended. So what these are the very simple procedure initially people use to get the straight line domain. Okay, the slope is independent of the flow rate. This is the advantage of the representation. The results obtained with different flow rates can be compared on the same graph. Okay, to find an expression of m which is dependent on the flow rate comparable to what is obtained with Horner's method, the superposition function needs only to be divided by the last flow rate. So what is now the things are initially people have just tried to understand things in a very simplistic manner. What by different changing different functions, they try to get a straight line domain so that the reservoir behaves homogeneously. Okay, but with time it has been understood that it is not going to be a straight line in each and every case. So that's why initial part, now these are the old methods actually people use to get either the skin, the parameters, or maybe the reservoir normal K. So by using the straight line domain, it has been done and it has been practiced. But now things have changed. Now things have changed. Now people are trying to get so if the last flow rate variation, if you just see, okay, so you have a superposition time as functions and your pressure. So it's a semi-log plot just to understand the straight line domain. What is straight line domain? Straight line domain is nothing but the compressible zone, that means is related to the Q, and the Q is supported. That means the area where the compressible zone has reached actually is supporting very nicely. That means it is infinitely acting domain, and from that we are trying to get the values of our normal reservoir K, and by using that we try to get the skin parameter skin. Okay, so this was done initially, and this is still many people are doing it, but now people all over the world, people are not following it. Okay, so agreed. So now we can discuss regarding our part. So you just okay, so now I am